Welcome. Today we are talking about deadlocks in operating systems. This is when processes get stuck waiting for resources. This concept is critical for understanding how operating systems manage multiple tasks efficiently.
What deadlocks are, why they happen, and how they are solved. By learning this, you'll see how operating systems prevent delays and keep systems running smoothly. Let's get started.
A deadlock is a situation where two or more processes are waiting for each other to release resources, and as a result, none of them can proceed. Imagine there are two processes P1 and P2. Each is holding a resource and waiting for the other's resource before it can continue. This creates a circular waiting scenario that can freeze part of the system.
Think of it like cars on a narrow road. Car A and car B are both trying to cross from opposite directions. Each waits for the other to move, but neither one can go. The cars are blocked. Just like these cars, processes also get stuck waiting indefinitely. Deadlocks can cause serious shutdowns in computer systems if not handled well. Let's consider a specific example. Process P1 holds resource R1 and requests resource R2, while process P2 holds resource R2 and requests resource R1. Since both processes are waiting for resources held by the other, neither one can proceed. This is a deadlock. This simple case demonstrates how easily deadlocks can occur even with just two processes.
Let's use the road analogy. Car A is on one side of a two-way bridge and car B is on the other. Both cars want to cross but cannot because each is blocking the other one. Similarly, processes in a deadlock cannot move forward until at least one releases a resource. Four separate conditions must exist for a deadlock to occur. First is mutual exclusion. This is when a resource can only be used by one process at a time. Like in our example, a single lane bridge. Only one car can cross at a time. Second is hold and wait. This is when a process holds at least one resource and then waits for another. Similarly, a car occupies the bridge and waits for the next section to be filled.
No preemption. Resources cannot be forcibly taken from a process, just like you cannot push a car off the bridge. Circular wait. A set of processes are waiting for each other in a loop. Imagine four cars in a circular road junction, each waiting for the next to move. If any of these conditions is removed, a deadlock cannot happen. The traffic can eventually move and the processes can continue. These conditions help system designers understand what to avoid.
Deadlocks can be managed mainly through detection and avoidance. In detection, the system allows deadlock to occur but periodically checks for them. Think of it as a traffic camera identifying cars stuck in a jam.
When a deadlock is detected, the system can recover by terminating one of the processes, similar to removing a car from the road, or by preempting resources like redirecting traffic. In avoidance, the system ensures resources are allocated in a way that never leads to deadlocks. For example, the banker's algorithm checks whether granting a resource request will keep the system safe. It's like a traffic controller planning movements to prevent jams before they happen.
To prevent deadlocks, we can just break one of the four necessary conditions. Prevention ensures processes never get stuck, just like traffic rules prevent cars from blocking each other.
Allow preemption. The system can take resources from a process if needed, like redirecting a car to another route. Prevent circular wait. Impose an order on resource request, just like traffic signals prevent cars from forming a circular jam. Avoid hold and wait. Force processes to request all required resources at once, like cars needing the full route available before entering. These strategies make systems more reliable and efficient. To summarize, a deadlock is when processes are stuck waiting for each other's resources, just like cars blocking each other on a narrow road. Understanding this helps prevent system slowdowns and freezes.
This covers the four necessary conditions: mutual exclusion, hold and wait, no preemption, and circular wait, and methods to detect, avoid, and prevent deadlocks. Mastering deadlocks allows us to design reliable, efficient, and stable operating systems. Thank you for watching.